Now I'm going to show you how to design the digital control of the buck converter. So we'll start with a live demo. In this case, the design of the control loops of the digital platform represent a great challenge for the controls engineers. Yeah, in this case we have to contemplate some blocks. For example, we have to consider the ADC gains, the transport delay of your control, etc., the sample period, etc. In this example, we proceed to design the control loops of the buck converter using the SmartCtrl equation editors in order to define the converter plan. So the first example I want to show you is if we start from the predefined topology. I want to export the results to the PSIM template. After that, we repeat the procedure, and we want to show you how to use the equation editor in order to get the same result that with the first example. So in the control structure, this is a synchronous buck converter. Here, we want to design the control loop in order to control the output voltage. So in this case, we have to consider the analog sensing chains, because the sensed voltage has to be in the range of the ADC span. For example, if we have our output voltage is 24 voltage, we have to reduce this voltage in order to stay inside the ADC span. The ADC span typical values are from 0 to 3.3 volts, or maybe from 0 to 5 volts, for example. After that, we have some sample and hold that is represented by the ADC. And here we have to consider the gain of the ADC, that it's depend on the bits number. So here we have to calculate the error, and then we have a PID compensator, and also we have the modulator in a digital platform. So all these blocks are inside the FPGA or the DSP. So in this case, in order to design the control loops, we have to consider, for example, well, also it's obvious that we have to consider the compensator transfer function. We have to contemplate some delay due to the digital control. We have to consider also the modulator gain. This is the plant of the converter. In this case, in the buck converter, this is the converter plant of the output voltage. We also have to consider the analog sensing chain transfer function, and finally the gain of the output volt, the gain of the ADC. So this is a digital delay concept. Here we have in this example we are considering a sawtooth carrier. We have a frequency sampling frequency equals to the switching frequency. In this case, we are sampling one. We have one sample every switching frequency. Also, in this picture, you can see that we sampled the output voltage when the carrier at the beginning of the carrier signal. So the digital control are formed with two parts. The first one is related to the calculation that we called T control. So in this case, we have a T control equal to one switching frequency, because we have from this point to this point in order to calculate that it is the time that your compensator and the conversion time you have to need. So after that, we have the time related to the modulator, so the digital PWM modulator. So in this case, this time is related when we have the control signal, the instant when the control signal is updated, it is updated. This means that this is the time when the control signal intersects with the carrier signal. So in this example, we have that the DPWM delay is related to the duty cycle. So in this case, is the duty cycle, because it's this width duty cycle per by the switching period. So after that, I want to open the smart control. Okay, let me. This is the initial dialog from the smart control, and here I want to select the DC-DC converter single loop, the voltage mode control or the current mode control. So after that, I have to click on in the checkbox of the digital control here. So now I have to define the converter topology. In this case, I select the buck converter, the first option. Here, I have to set the input parameters. In this case, I consider input voltage of 100 volts. The parasitic resistance of the inductance is equal to 10 milliohms. The inductance I consider 15 micros. The capacitance is 100 micros. The output powers is equal to 500 watts. The switching frequency, I said 100 kilohertz, and the output voltage 24 volts. If I click on calculate, you can see here the operating point information. So the duty cycle is equal to 0.24. You can see also the average current, the peak value of the current, the inductance current, and the value of the inductance current. So after that, I click on OK. So now it's time to define the sensor stage. In this case, I select the isolated V sensor, voltage sensor. So as I mentioned before, here we have to reduce the sensed voltage in order to stay in the ADC span. So in this case, I set again equal to 0.125. If I click on calculate, you can see now that our reference voltage is equal to 3 volts. So in the H pole, also you can, if you want to use anti-aliasing filter, here I set, for example, the 50 kilohertz. Okay, now we have to click on OK. And in this case, we can select one of the options of the compensator. So if I want to design a PID compensator, I select this option. And now it's time to define, for example, this is in the digital PWM box. You can select different type of carrier. In this case, we have the trailing edge because it's a sawtooth carrier. And this is represent the peak maximum value of the sawtooth current. In this case, if you have, for example, 12 bits, you can set this value, the 4096. So after that, we have to define the ADC span. So here, the minimum voltage is 0, and the maximum, for example, I set 3.3 volts. Also, you can define the bits number. So in this case, I set 12. This is the sample frequency. As I mentioned before, I want to take one sample every switching frequency. So in this case is 10 kilohertz, and testing is related to the digital delay. So in this case, I said 10 micros. That means that a smart control get the digital delay from the intersection between the control signal and the carrier signal. This is the point when we update the control signal. So the sample is this one. So if you can see here, this sample is take from 10 microseconds, and the control signal, the gate signal is updated at 20 microseconds. So we have 10 microseconds here. If I set, for example, 8 microseconds, and click on update, you can see how this picture is updated automatically, and the difference between these points are related to the 8 seconds. From here, from the green line to the orange line to here. Okay, in this example, I set 10 micros and click on update. After that, I click on OK. So now we have to select one point of the solution maps. So here you can also set directly the crossover frequency. In this case, I set 6 kilohertz. And for example, the phase margin, I set 50 degrees. So click on OK, OK, and after that, click on OK. So now this is our result of the design. This is the solution maps, and here we have the crossover frequency. So you can see here, we have the open loop frequency response, and the intersection with the 0 dBs in this case is at 6 kilohertz. That it's according to the crossover frequency, and also we have a phase margin of 50 degrees. So we have the option to export directly to the PSIM, PSIM. In this case, I set a name, like for example, test one. Test one, click on open. Directly, the option that is exported is in the transfer function is implemented with the seed block. So click on OK. And now here we have to connect the reference of the output voltage. In this case, we reference directly to the ground. So after that, if we want to click on the simulation to simulate, and I want to show you the output voltage, you can see that the output voltage achieved the reference. So we have the 24 volts. So after that, in order to check if the crossover frequency is the same like the SmartCtrl predict, I want to do a AC sweep function. So in this case, I want to add the AC sweep block. I want to inject some perturbation here before the ADC. So this is the sensing voltage. I have to select a sine source. Okay. I set the peak amplitude 0 volts, frequency equal to 0, and the name I want to change to SIM1. So in the AC sweep parameters block, I want to set the start frequency to, for example, 8 hertz to 40 kilohertz. The name of the source name has to be the same for this element. So BSIN1 and the AC sweep function BSIN1. Okay, and the amplitude of the perturbation equal to 0.01, 0.01. Okay, so we have to connect these to in order to calculate the error, and also we have to select the AC sweep proof, the loop option. So in this case, I want to put here. And now we can get the frequency response of the open loop transfer function. So this will take some minutes, well, seconds, I think, in this example. So we have to wait a little bit. Okay. So now I want to save this information. If I go to File, Save As. Okay. Here I have to put some name, PSIM. I want to save as txt file. Click on OK, save. So now if I open a SmartCtrl, if I go to File, to the option Import Merge, we can combine some transfer functions. So in this case, I want to click on add, select the open loop transfer function. I want to change the color to blue. And also you can select the txt file. So in this case, I select maybe it's this one, PSIM. Okay, click on OK, and click on OK, and finally apply. So here you can see that the frequency response obtained from the PSIM match with the frequency response that it's predicted by the smart control. So this control design have a crossover frequency or crossover frequency equal to 6 kilohertz, and the phase margin is equal to 50 degrees. So another option that I mentioned before, the second example, if I want to define the converter plan directly from the equation editor. In this case, I click on File, New, go to this icon, and here, this is the equation editor window. If you click on editor, here we can write the transfer function. So in this case, I have the equation already here. So this is the buck converter plan. So here, this is the buck converter transfer function. In this case, we always have to set the return function in order to plot the frequency response of the converter plan. So after that, I click on OK. I have to define the sensor equation, the sensor state. So also you can define the sensor state using the equation editor. In this case, this is the second part. So we have a simple low pass filter. Maybe I want to paste here. So this is a simple low pass filter. You have the gain, the crossover frequency, and you have one pole here. So click on OK. Also, you have to text the return and click on OK. So this is the transfer function. Click on OK. And now we can select the digital option, for example. So here we have to select the PID, and we have to select the same parameters that equals to the last example. So here I set 3.3 volts, 12 the bits number, the sample frequency, the duty cycle. In this case, I set that the duty cycle is equal to 0.24. And now click on update. So click on OK. We have to select the same crossover frequency, 6 kilohertz, and the phase margin equals to 50 degrees. Click on update, click on OK, and OK. And you have the results. So in this case, I want to import the same transfer, the same frequency response that I obtained from the PSIM software in order to check if the frequency response is the same. So in this case, I select the TPSIM. I want to change the color to blue, click on OK, finally apply. So here you can see that the frequency response is the same, match in both cases. So this is another way if you want to define your converter plan using the equation editor. So this is a very useful tool, because you can, with this tool, you can design the control loop for any type of power converter electronics. So this is all. And if you have any question, let me know. Thank you.